Jai Hind everyone. I'm Shruti Jain, Assistant Professor, MCA Department, Ajay Kumar Garg Engineering College, Ghaziabad. The topic that I'm going to discuss today is the critical section problem in operating system. The subject code is BMC 203 and the subject is operating systems. The students for which this topic is being covered is MCA second semester students. So let us first understand what the critical section problem means. So let's suppose that we have a system where we have n processes that are entering into the system. The processes are numbered from P0 to Pn-1. That means there are n systems. Now, each process that is entering into the system would have a segment of code that is known as a critical section, in which the process may be changing some of the common variables. It may be updating a table, writing a file, or maybe doing some of the work which needs a change in the code. Now, when the process executes the code which manipulates the shared data or any of the resources that a system holds with it, we say that the process is in the critical section for that particular shared data for which that code is running basically. So, the important feature of the system is that when one process is executing in the critical section, no other process will enter into the critical section and would access that shared resource on which that the current process is actually working on. That is, no two processes would be executing into the critical section at the same time. So, the execution of the critical sections it includes the mutual exclusion. Mutual exclusion basically says that at any point of time, only one process is allowed to execute into the critical section, even if we have multiple CPUs. So, for example, if we have suppose two processes that are entering into the system at the same time, and the first process enters into the system and holds that critical section area, P2 has to wait till the time P1 releases that critical section and makes it free for the P2 to enter into the critical section and do the execution. So, the critical section problem is to basically design a protocol that the processes can use to cooperate. Each process must request a permission whenever it wants to enter into the critical section. It is not the case that as soon as a process enters into the system, it will get the critical section. Every process has to raise a request that it wants a critical section for the execution. Once that request is granted, only then the process can enter into the critical section and do the execution. So, if we look over here, we have this as a code wherein we have the entry section for every process that is entering into the system. Once a process enters into the entry section, it will execute this critical section and will stay into the critical section till the time it is making any change into the code. Once that critical section is executed, then it exits from the critical section. So, we have the exit section. This is a remainder section which is independent for this process only. For example, this critical section is having multiple resources which are shared by multiple processes. So, we have P0, P1, P2, all the processes wants a particular resource that is there in the critical section. So, each of the process has to wait for the other process to release the critical section. But remainder section is a section which is independent for each of the process. That means if P0 enters into the remainder section, that means it is independently running and independently working only on the resources that this P0 needs. Now, P1 and P2 do not play any role in the remainder section. The critical section problem is to design a protocol that the processes can use so that their actions will not depend on the order in which their execution is interleaved, maybe on multiple processors. So, if we look onto the framework for the analysis of solution, each process executes at a non-zero speed, but no assumption on the relative speed of n processes. The process must be an executing process. Number 2, many CPUs may be present, but the memory hardware prevents simultaneous access to the same memory location. No assumption about the order of the interleaved execution, it could be in any order. For solution, we need to specify the entry and the exit section. The process needs to take the permission to enter into the entry section, and it needs to notify that it is now entering into the exit section so that other processes can enter into the entry section. So we have the solution to the critical section problem. The first solution that we have is, or the critical section problem, it must satisfy the following three requirements. The first one is the mutual exclusion. Mutual exclusion basically says that if one process is entering into the critical section, no other process should remain into it, or no other process can enter into the critical section. In other words, only one process can enter into the critical section at one point of time. The next one is progress. If no process is executing in its critical section and some processes wish to enter their critical section, then only those processes that are not executing in their remainder section can participate in deciding which will enter into its critical section next. For example, like we have seen over here, if there is any process that is currently working into the remainder section, now it again wants to enter into the critical section, then, and suppose this process is P5. P5 is currently running into the remainder section and it wants to access the critical section over here. Then P5 will only be allotted the critical section when it will exit from the remainder section. That means it is not executing anything into the remainder section and is purely waiting for the critical section. So that is progress. Bounded waiting. There exists a bound or a limit on the number of times the processes are allowed to enter into the critical section after a process has made a request to enter its critical section and before that request is granted. So it is not the case that every process will be entering into the critical section unlimited number of times. There is a bound or there is a limit, and the process can enter into the critical section for a fixed number of times, not multiple number of times. So here we assume that each process executes at a non-zero speed, as we have already discussed previously, and there is no assumption based on the relative speed of n processes. So we have two general approaches that are used to handle the critical section problem. The first one is the preemptive kernels and the second one is the non-preemptive kernels. Preemption basically means when a resource is allocated to something and that is forcefully taken up from that particular process or the kernel. That is basically known as preemption. Non-preemption is once allotted, it will only be released once the work is done. So a preemption is an act of temporarily interrupting a task being carried out by a computer system. So a preemptive kernel allows a process to be preempted. That means the resources can be taken, the process can be taken while it is running in the kernel mode. A non-preemptive kernel, it does not allow a process running in the kernel mode to be preempted. A kernel mode process will run until it exits the kernel mode. So the non-preemptive kernel is as soon as a process enters into the kernel, it has to execute completely, only then it will exit. But in preemptive kernel, the process can be interrupted in between if any other process enters into the system which may be of higher priority and it can be given the execution first. We have multiple solutions over here. The first type of solution that we have is a software solution. Software solutions are the algorithms where the correctness does not rely on other assumptions, any other assumptions. When we talk about the hardware solutions, they rely on some special machine instructions. We'll look into it in the later slides. Then we have operating system solutions. They provide some functions and the data structures to the programmers. So we have the first algorithm, that is the Decker's algorithm for the critical section problem solution. So whenever we are talking about the critical section problem, we normally consider two processes that wants to take the critical section at a point of time. Now, how the decision between the two processes is to be made is being explained over here in the Decker's algorithm. So here we have two processes, the process Pi and the process Pj. These two processes wants to enter into the critical section and do the execution. We have a variable, that is a flag variable. The flag variable is always set to true as soon as the process wants to enter into the critical section. When the process does not want to enter into the critical section, the flag is set to false. So here, initially the flag of the process Pi and Pj is set to false. That is the initial one. Then we have the variable turn. The turn variable decides which process has its turn to enter into the critical section. So initially that turn is also 0. Now, when a process Pi wants to enter into the critical section, as soon as the process enters into wants to do the execution, it will set its flag to true. So as soon as the process Pi enters into the system, it sets its flag to true, denoting that now it is ready to access the critical section. Now, because the process Pi and Pj both entered into the system and want to access the critical section, because Pj also wanted to access the critical section, the flag of Pj is also set to true. Every process will check for another process whether that process is there into the critical section or not. It will check two things, the flag and the turn. So it will check while flag j. While flag j means while the value of flag is true, which is already over here. It will check if the process Pj wants to access the critical section, number 1. Also, is there the turn of the critical section for process Pj only? Then it will wait. Otherwise, it will enter into the critical section. So it will check while flag j. Currently, we have the flag j as true, and it will check the turn to be j or not. Suppose the process Pi enters into the system, the turn of the variable turn took the value as I. As soon as the Pi started execution, Pj entered into the system and put the value of turn as j. Now, as soon as the Pi started with this while loop, it checked that the flag is j and the value of turn as j. Here, the value of turn is j. So, once the value of turn is j, that means Pi cannot enter into the critical section currently. So, it will put its flag value to false. That means it is not eligible to enter into the critical section at this point of time. And it will keep on waiting till the turn is j. The turn is j. In this case, what will happen to the process Pj? Now, the process Pj is flag j equals to true. This we have already seen. While flag I, because here this flag I has been set to false. So, here this flag I over here would be false. Now, since this while is false, it will come out of this loop from here. Coming out of this loop from here means Pj enters into the critical section. Now, when Pj enters into the critical section, here Pi is waiting because the turn is of j. Pj over here is entering into the critical section and working and getting the execution done. Once the critical section is over, its work for the critical section is over, what it will do? It will put the turn to I. Now, when this turn is set to I, let's see what happened over here. As soon as this turn is set to I, this turn becomes I, because this is shared variable. This turn becomes I. Now, as soon as this turn becomes I, this waiting is stopped now. Now, I is no longer waiting over here. I no longer waiting over here means now the critical section is free. So, it will set its flag value to true. Once the flag value is set to true, it will again go and check for the while. Meanwhile, what will happen over here? It will turn the value of turn to I and it will make its flag value to false. Once the flag value becomes false over here, this while block becomes false. This while block becomes false means it will come out of this while and I enters into the critical section. I enters into the critical section. By that time, maybe some other process entered into the system. It will put the turn to that particular process and make its flag value to false, denoting that now it no longer needs the critical section enters into the remainder section and moves out of the system. So this is how the Decker's algorithm works. So here we have turn as a global memory location that both the processes could access. Each process examines the value of the turn. If it is equal to the number of processes, then the process could proceed to the critical section. This process is known as busy waiting, as we have seen that till the turn value is j, in that case a process pi is waiting, and till the time the turn value is I over here, the pj is waiting over here. Since the processes are waiting to get the access to the critical section. We have another algorithm, that is a Peterson algorithm, which is just a change overcomes the problem that we face over here. The problem here in the Decker solution is, in case both the flag values are set to true, now what happens is, here I makes its value as the flag is true for both of them. Now the turn becomes I over here, and this turn becomes I. In that case, what happens? Here it enters into the true value and the turn here is I, but the flag j becomes false. Let me explain it again. The flag value here is j, because in that case what is happening over here? The turn is also to be of j. In case the turn is of I over here and the flag value of j is set to true, the loop will go on endlessly. So in that case, if the turn is of I and the flag value of j is set to true, in that case it will enter into the loop for infinite number of times. Because the value of j is, flag value is true, the turn is of I, it will not enter over here, it will keep on moving into this loop again and again. When flag value of j is true and the turn is of I, in that case, none of the process enters into the critical section. So this problem is overcome by the Peterson algorithm. The Peterson algorithm, what it does is, it again has a flag variable, it has a turn variable, but when it is checking the condition, it is checking both the conditions together into the while statement over here. So what happens over here? We have the processes pi and pj like we had earlier. Both the processes set their flag value to true as they enter into the system to do the execution or to access the critical section. Now here what happens? Instead of checking whether the turn is of process pi or of pj, every process puts deliberately the turn for the next process. That is, if the process pi is there, it will set the turn variable to j into its code. Similarly, if process pj is there, it will set its turn value to I deliberately. So in that case, the problem that we were facing into the Decker's algorithm, this problem will be solved over here. Now it will check while flag j, that is whether the process pj is trying to access the critical section and whether the turn is of also j. If both the conditions are true, then pi will keep on waiting. In case the flag value of j is false or process pj does not want to access the critical section, in that case, the process pi will not wait. It will enter into the critical section, do its execution. Once it completes its execution, it keeps its flag value to false, enters into the remainder section and execute. In case pj, the process pj sets its flag value to true and the turn is again of j, in that case pi will keep on waiting. Pi will keep on waiting. In that case, what will happen? Here this condition becomes false because turn is of j. Flag I is true, but turn is of j. In that case, it will not wait over here. It will enter into the critical section. It will keep on processing till pi will be waiting over here. Once the critical section is done, it sets its flag value to false. As soon as it sets its flag value to false over here, this flag value becomes false. It exits from the waiting area and enters into the critical section. Meanwhile, process Pj enters into the remainder section over here. So this is how both the processes manages which process will enter into the critical section, and only one process enters into the critical section at one point of time. So in the Peterson solution, we have it is a two process solution where we have two variables, turn and flag. The turn indicates whose turn is to enter into the critical section. The flag array indicates if a process is ready into the critical section. Flag I equals to true implies that the process Pi is ready. It meets our requirement assuming that each statement is executed atomically. Considering the Peterson solution, it is used to synchronize two processes that we have just seen, where initially the flag values are false. As soon as one process enters into the system, it sets its flag value to true, make the turn of the other process to give the turn to other process for the execution, and then it checks its condition in the while loop. If the flag is true and the turn is also of the other variable, in that case it will wait, otherwise it will enter into the critical section and do the execution. So that is all for today. Thank you.